Famous physicist Brian Cox has just announced that our universe exists inside of a black hole. Black holes are interesting because we have a place called the event horizon where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature, quantum theory and general relativity. The quest to unify these two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is, in some sense, a holy grail for theoretical physicists. According to physicist Brian Cox, something terrifying existed before the Big Bang. The prevailing idea is that the universe, in a sense, was cold and empty before undergoing an extremely rapid expansion. This expansion eventually slowed down and stopped, releasing energy that heated up space and created the particles that form everything we see today. This event is what we refer to as the Big Bang. However, the concept of what existed before this event has left scientists both fascinated and terrified. One theory that extends this idea is called eternal inflation, which suggests that inflation, the rapid expansion of space, continues indefinitely, stopping only in small patches. Each of these patches represents a Big Bang in a universe, with our universe being one of them. This leads to the idea of an infinite fractal universe filled with countless Big Bangs, known as the inflationary multiverse. In the vast cosmos, the notion of absolute nothingness seems more theoretical than real. Even if all energy were removed from the universe, it wouldn't be truly empty. The universe is currently filled with matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even in the absence of energy, the universe continues to generate new forms of energy, a phenomenon that confounds our understanding. It appears that the universe doesn't align with our concept of complete emptiness. If all energy were removed, leaving a void, one might expect the universe to reach absolute zero, with no particles or activity. However, this isn't the case. Even in an empty universe, its expansion would still produce radiation extending far into the future, or even back to the time before the hot Big Bang. This suggests that the universe never truly becomes void. Given this, is it plausible that the universe originated from nothing? While we can't be certain, it's clear that something always persists. Even if particles, antiparticles, photons, and quanta are removed, empty space remains. If we eliminate all external influences, such as electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a kind of physical emptiness still exists. In this space, quantum fields endure, along with the fundamental constants and laws of physics. There is an inherent, finite, positive, and non-zero value of zero-point energy in that space, representing the closest approximation to nothing within our universe. While one might imagine an even more nothing-like state, it lacks physical reality, as no experiment can replicate such a condition. By adhering to scientific principles, we acknowledge that something always exists because true nothingness cannot coexist in our universe. Yet, the question of why remains unanswered by science. Our universe today is far from empty. It's teeming with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation from both starlight and the remnants of the Big Bang. With improved observational tools, we could potentially detect additional signals, such as gravitational waves generated by mass moving through changing gravitational fields, mysterious signals from dark matter, and a broader perspective on black holes. Everything we observe occurs in a universe that isn't static but is continuously changing. From a physical standpoint, it's fascinating to comprehend the evolution of our universe on a grand scale. The fabric of our universe, known as space-time, is expanding. This means that as time progresses, the distance between 2 points in spacetime increases, as does the time it takes for light to travel between them and the wavelength of that light. The universe isn't just getting bigger, it's also getting colder. As it expands, light stretches to longer wavelengths, moving toward lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. During this process, objects with mass or energy attract each other, forming clusters and creating a vast cosmic network. If we were to remove all matter, radiation, and energy from the universe, what would remain is essentially empty space itself. still expanding, still governed by the laws of physics, and still influenced by quantum fields. This is the closest physical approximation to true nothingness, yet it still adheres to specific physical principles. To a physicist, removing anything else would create an unrealistic state that no longer reflects the cosmos we inhabit. This suggests that dark energy, as we currently understand it, would still be present in this hypothetical universe devoid of mass. In essence, if every quantum field in the universe was set to its lowest energy state, we would arrive at the zero-point energy of space, where no additional energy could be extracted for mechanical work. In a universe containing dark energy, a cosmological constant, or the zero-point energy of quantum fields, it's plausible that the zero-point energy wouldn't be truly zero. As the universe continues to expand and cool, there will come a time in the distant future when radiation becomes the dominant component, surpassing other forms of matter and energy, leaving dark energy as the primary influence. However, there was also a period in the universe's history, not in the future but in the distant past, when something else besides matter and radiation held dominance. During cosmic inflation, prior to the hot Big Bang, our universe underwent extremely rapid and constant expansion. Instead of being dominated by matter and radiation, the cosmos was controlled by the field energy of inflation, akin to today's dark energy, but much more potent and expanding at a significantly faster pace. If eternal inflation is accurate, but time remains, where might the universe have originated? There must have been a beginning, correct? To address this question thoroughly, let's unravel three commonly conflated concepts: the hot Big Bang in relation to our universe, the theory of cosmic or cosmological inflation, and its role in preceding and preparing for the Big Bang, and the issue of an ultimate beginning or origin for our universe. In the early 20th century, a significant synthesis took place when four key pieces of information came together. Alexander Friedmann's breakthrough in Einstein's general relativity showed that a universe filled uniformly with any form of matter and energy cannot remain static, but must either expand or contract. Henrietta Leavitt's observational work established a connection between the period of brightness and dimness of variable stars and their inherent brightness. Vesto-Slipher's measurements of the redshift or blue shift of light from spiral and elliptical nebulae indicated that these galaxies were moving away from us at high speeds. Finally, Edwin Hubble's confirmation of these findings led to the concept of an expanding universe. If the universe expands, it suggests that over time, space itself stretches, causing the matter within it to become less dense. As space expands, radiation like light waves not only becomes less concentrated but also stretches, leading to the universe cooling. If we rewind the clock, the opposite would occur. In earlier times, the universe was denser and hotter. If we rewind further, all matter and radiation would have been squeezed into a smaller space, increasing the density of the universe. The light, which stretched due to cosmic expansion, would have had a shorter wavelength, resulting in hotter temperatures. If we envision going back as far as physics permits, we'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The initial idea of the Big Bang theory resulted in the formation of 5 key expectations regarding the early universe's hot and dense conditions. These forecasts became the foundation of the Big Bang theory. The universe ought to demonstrate expansion. Initially, it should have been relatively uniform. In the past, it was hotter, atomic nuclei couldn't form stably, and neutrinos played a significant role. With strong observational evidence supporting these predictions, the Big Bang theory has remained uncontested as the primary explanation for the early universe since the mid-1960s. However, as evidence supporting the hot Big Bang theory grew in the 1960s and 1970s, certain challenges surfaced that the Big Bang alone couldn't resolve. These challenges include the horizon problem, the flatness problem, and the monopole problem. Alan Guth introduced a solution to these cosmological mysteries in 1980 with a groundbreaking paper suggesting that an early phase of rapid and continuous expansion called inflation could solve all three issues. Inflation not only explains these phenomena, but also presents a compelling alternative to the standard hot Big Bang model. Additionally, inflation acts as a quantum mechanism for seeding the universe with initial imperfections, ultimately leading to the intricate formations we see today. Inflation theory made precise and testable forecasts about the beginnings of cosmic structure that have been validated by observations spanning from the 1990s to the present day. Notably, inflation involves a rapid expansion of space rather than culminating in a singularity like the original model for the Big Bang. This raises a fundamental question about the actual beginning of the universe. If eternal inflation is accurate, it suggests that while inflation ends in certain areas, there will be countless more regions where inflation continues, creating more space that keeps expanding. However, eternal inflation has limitations. It's eternal only into the future, not into the past. In fact, it's been demonstrated that inflationary spacetime doesn't extend into the past infinitely and must have originated from a prior non-inflationary and possibly singular state. While the hot Big Bang is our most accurate model of the early universe, it wasn't its absolute genesis. Prior to the hot Big Bang, there was a period of cosmic inflation which initiated and led to the hot Big Bang. Unfortunately, our knowledge of the state before inflation is limited. The universe is filled with energy fields that interact to form everything we see. Quantum field theory, one of the most accurate theories in physics, describes the universe as being made of energy fields that permeate space and interact, creating everything we observe. These fields are constantly moving due to quantum fluctuations, and even in their lowest state, known as the vacuum state, fields remain active. Virtual particles continuously borrow energy from the vacuum, briefly appear, and then disappear. When the field is excited, it produces elementary particles that persist and interact, forming the world we know. The type of particles created depends on the field, with different matter particles associated with specific types of fermions. These fermions interact through force fields such as electromagnetism, the strong nuclear force, and the weak nuclear force. The Higgs field, which gives mass to other particles, is also a crucial component of this framework. All fields, including matter and force fields, exist everywhere but interact differently, leading to the complex structures we observe. The creation of matter particles is an exception. An atom forms when there's enough energy in the quark fields to produce quarks that aren't destroyed by antiquarks. Gluons, particles related to the strong force, bind quarks to form protons and neutrons, which then create a nucleus. Physicists propose that the visible universe consists of remnants that survive the constant creation and destruction of virtual particles. However, the particles making up dark matter remain a mystery. The universe is full of virtual particles, but this doesn't completely negate the idea of nothingness. There's the nothingness before the Big Bang, which we don't yet understand, and the nothingness made up of vast fields of quantum energy that produce matter and force, leading to the creation of our world. Lawrence Krauss, in his book A Universe from Nothing, argues that the inherently unstable nature of nothingness produces elementary particles. There's also the idea that the entire universe might be a large virtual particle, as proposed by the vacuum genesis hypothesis, which suggests that the universe began as a large fluctuation in the nothingness that preceded it. Ultimately, everything, you, me, the whole universe, amounts to a big bunch of nothingness. Even if you can picture an empty universe, this doesn't match reality. Adhering to the laws of physics is enough to dismiss the idea of a truly empty universe. As long as there is energy within it, even the zero-point energy of the quantum vacuum, there will always be some form of radiation that can't be eliminated. The universe has never been completely empty, and as long as dark energy exists, it never will be. The universe is the way it is, and while we try to understand it as much as we can, we should remain humble in the face of its vast unknowns. My only advice is to embrace the curiosity that drives us to explore, question, and uncover its mysteries.